The first type of function that we are going to review is the absolute value function. So we're going to take a look at some absolute value functions. Of course, we've already reviewed linear functions. That would be the natural place to start. But since we've already reviewed those in Chapter 1, let's take a look at absolute value functions now in Chapter 2. So first of all, to wrap our brains around the absolute value, there are a few different ways that we could define what we mean by absolute value. One way that you may have been taught in the past is that the absolute value of a number is the distance of that number from 0 on the number line. So for example, absolute value of 5 and absolute value of -5 are both 5, since each of those numbers is 5 units away from 0 on the number line, right? So 0 is here, 1, 2, 3, 4, 5 is there, 1, 2, 3, 4, -5 is there, and so both of these numbers are 5 units away from 0, and that's why the absolute value of each of those numbers is 5. So that's one definition. It's a fine definition. Another way to define absolute value is to use this equation, right? Absolute value of x is defined to be the square root of x squared. That's maybe a little bit more strange to you, but to show you that it still works, using this definition to calculate absolute value of 5, we would say, well, this is the square root of 5 squared. 5 squared is 25, square root of 25 is 5. Meanwhile, absolute value of -5, this would be square root of -5 squared. -5 squared is -5 times -5, that's still positive 25, and then square root of 25 is 5. So that definition also works, right? It's also a good definition. The long and short of both of these procedures is that absolute value of x takes negative real numbers and assigns them to their positive counterparts, while it leaves positive numbers alone. Okay? So I think you probably have a pretty decent understanding of absolute value. So I'm going to let you work on these 6 problems, see if you can calculate each one of these things. So go ahead and give the video a pause and see if you can work them out. Okay, I'm just going to kind of run through them. Absolute value of 3 is 3. Absolute value of -3 is also 3. Negative absolute value of -3 is going to be -3, right? Because absolute value of -3 makes this thing 3, but the negative sign on the outside still has to come along for the ride. Let's see. This is going to be -8 inside of the absolute values, so then when you take the absolute value, you get 8. This one, on the other hand, well, you take the absolute values before you do the subtraction, right? So you're going to get a +3 minus a +5, and that's going to give you -2 overall. And then part F is the same thing as part E, but just with a bigger set of absolute values, like a double set of absolute values, I guess. So this thing would be the absolute value of a +3 minus 5, which is going to be the absolute value of -2, which is going to be +2. Okay. So that's the idea behind absolute values. Now, we want to take a look at absolute value functions. We want to know what their graphs look like. We want to be able to solve absolute value equations and all of that stuff. So first of all, as far as graphs are concerned, so from the introduction to this section, you should know that the absolute value function looks like this. It's a little V shape, okay? There are certain points on this function that I want you to transform when we go to graph transformations of the function, and we reviewed transformations a little bit in Chapter 1, right? But the points that I want you to transform are these. So definitely 0, 0, right? 0, 0 is a special one. It's the vertex of the thing. So that's going to be a very important point. But then in addition to that, I want you to plot a couple points to the right, so 1, 1, and 2, 2, and a couple points to the left, so -1, 1, and -2, 2. But of course, these points are going to have to be transformed so that they match the function, right? These are the points that are on the graph of f of x equals absolute value of x. But if you were looking at a graph like absolute value of x plus 3 minus 2, then you're going to have to transform these, right? So let's practice doing that. Absolute value of x plus 3 minus 2 is going to take each one of these points and it's going to shift them left 3, down 2. So 0, 0, instead of being at 0, 0, right, it's going to go left 3 and down 2. So there's my new vertex, right? And now the rest of the points you can do a couple different ways. One of the ways you could do it is you could say, well, I'm going to just do the same thing for each one of the points that I did for the vertex, right? So I'm going to take 1, 1 and shift it left 3 and down 2. And I land there. The other thing you could do is you could just realize that the whole graph is going to get shifted around together as one cohesive unit. So if the parent function looks like this, right? If that's what the parent function looks like, then the new function is just going to be this whole thing shifted down to left 3. And so then you can kind of figure out that, oh, well, so the other points must just look like this, right? Anyway, so you get something like that. Okay, so that's that one. Part B is maybe a little bit more complicated because in addition to doing some horizontal and vertical shifting, you're also going to be doing some vertical stretching and reflecting, right? So what this thing is going to do is it's going to multiply all of our y coordinates by 2, and it's going to flip them over. So the vertical space between this point and this point is going to be doubled, and it's going to be reflected. So it's going to be pointing downwards instead of pointing upwards. So let's do this, right? So the vertex is going to go right 6, down 1. 1, 2, 3, 4, 5, 6, down 1. So there's my new vertex. And then this parabola is going to open down, and the vertical distance between the points is going to be multiplied by 2. So instead of the next point being here and then the one after that being there, right, kind of like this, instead of it going in that direction, it's going to be opening down, and the vertical distance is going to be stretched by a factor of 2. So instead of going over 1, down 1, I'm going to go over 1, down 2, right, to get to the next point. And then from there, I'm going to go over 1, down 2 more. Or if you like, from the vertex, you're going to go over 2, down 4, right? So that's what that's going to look like. Again, you could do this like point by point. So you could say, well, 0, 0. First, it's going to be shifted right 6. Then it's going to be multiplied by -2. The y coordinate is going to be multiplied by -2. Well, 0 times -2 is still just 0. And then it's going to be shift down 1, right? So that's where 0, 0 ends up. 1, 1. Well, first it's going to be shifted right 6. 1, 1. First it's going to be shifted right 6. Right 6. So it ends up there. Then it's going to be, the y coordinate is going to be multiplied by -2. So it's going to end up, instead of at +1, it's going to end up at -2. And then it's going to be shifted down 1. So it ends up right there, right where we placed it, right? And you could continue doing this for all of the other points on the graph, but that's what it's going to look like. To be perfectly honest with you, I don't really care how you do this, as long as you can do it. And you should be able to do this without using like a graphing utility, a calculator or Desmos or anything. You should be able to do this on your own. Now, since this is an online course, there's not going to be really any way for me to prevent you from using Desmos to do these kinds of graphs. But just know that like going into calculus, if that's your approach, if your approach is to just use Desmos and copy what Desmos says, then you're going to suffer in calculus. You're not going to understand the functions as well as you should. So practice doing them by hand. Okay, so that's how we graph those kinds of simple functions. But what if you have a function that's not exactly a transformation of an absolute value function, right? What if you have something a little bit more complicated, like something like this, for example, that's not just a transformation, because you have some x's that are in absolute values, but then you have some x's that are not, right? So what do you do with those? Well, for functions like this, when it comes to graphing these or solving equations that look like this, we need to introduce a new way to define the absolute value. So this is another way to think about absolute values that's going to be very helpful for graphing things like this. Okay, so the absolute value of a real number is denoted, well, the absolute value of a number can be defined in terms of a piecewise function in this way, right? We say the absolute value of x is going to be negative x if x is negative, and positive x if x is positive. Okay, think about it. If x is 5, then the absolute value of x should be 5, right? Well, so if we use this rule, absolute value of x, absolute value of 5, since 5 is positive, we're going to use the bottom rule, okay? And we're going to say, all right, so we're going to say 5, right? So absolute value of 5 is 5. Absolute value of negative 5 should also be 5, right? Well, since negative 5 is less than 0, we would use the top rule. So we would say absolute value of negative 5 is negative negative 5. Negative negative 5 is positive 5, right? So it works out, right? This definition still works. It still takes negative numbers and returns positive numbers, and it takes positive numbers and leaves them positive. So when we're dealing with more complicated functions like this, it's useful to rewrite them in terms of this piecewise definition, okay? And that goes for whether we're graphing them or solving equations. It's going to be useful for us to think about them in terms of this piecewise definition. If there's more than one absolute value, like in part B, then it's pretty helpful to like draw a number line and mark the places where the rule changes, okay? And then write a new piecewise function based off of that. So let me give you a couple examples because I know that this is kind of a strange concept at first. So looking at part A, we have f of x equals absolute value of x over x. So if I wanted to graph this function, I mean, I have no idea what this thing is going to look like, right? But I can use this piecewise definition to get a handle on things a little bit better. So if I think about f of x using the piecewise definition, I say f of x is going to be, well, the absolute value of x is going to be negative x if x is less than 0. So f of x would be negative x over x if x is less than 0. And then it would be positive x over x if x is greater than or equal to 0. Right? That's just using the piecewise definition. I can simplify that a little bit now. I can say, well, obviously, negative x divided by x is just going to be negative 1. And positive x divided by x is just going to be positive 1. Okay, so this is what I get from my piecewise function. F of x is going to be negative 1 if x is less than 0. And f of x is going to be positive 1 if x is greater than or equal to 0. So here's what that would look like. If x is positive, so for any of these positive values up here, f of x is going to be 1. So if x is 0, f of x is 1. If x is 3, f of x is 1. If x is whatever this number is, right, f of x is 1. So you get that horizontal line at 1. If x is less than 0, so if x is a negative number, then f of x is going to be negative 1, right? So if x is negative 2, f of x is negative 1. If x is negative whatever this is, f of x is negative 1. So you get this kind of function, right? You get a horizontal line there and a horizontal line there. Maybe the only thing we have to work out is how far over does this bottom horizontal line go? And the answer is it should go all the way to 0, but just not including 0, right? So we put a little hole there to indicate that. And that's what the graph of that function looks like. Okay. You're welcome to verify this in Desmos. So you can open up Desmos and type in absolute value of x divided by x, and this is the picture you're going to get. Desmos doesn't really show the holes in graphs, so it's not going to show an open circle there. But otherwise, it will look exactly like this. Let me give you another example. I'm sure you're confused by this. If you're confused by this, do not fear. We'll look at some more examples and hopefully unconfuse you. So let's look at another one, right? We have f of x equals absolute value of x plus 2 minus absolute value of x minus 3 plus 1. How in the world are we going to deal with this? Well, first of all, let's think about these in terms of their piecewise definitions. So absolute value of x plus 2. This is going to be negative x plus 2 if x plus 2 is less than 0. And it's going to be positive x plus 2 if x plus 2 is greater than or equal to 0. So let me simplify that a little bit. Right? That means that this is going to be negative x minus 2 if x is less than negative 2. Or it's going to be x plus 2 if x is greater than or equal to negative 2. Right? So that's what the absolute value of x plus 2 is. Absolute value of x minus 3 is similar. Right? It's going to be negative x minus 3 if x minus 3 is less than 0. And it's going to be positive x minus 3 if x minus 3 is greater than or equal to 0. So simplifying that a little bit, we're going to have negative x plus 3 if x is less than 3. And we're going to have x minus 3 if x is greater than or equal to 3. Okay? So now putting this together, this is where it's helpful to draw a number line and to mark where the rule changes, right? So the rule changes at x equals negative 2, and then it changes again at x equals 3, right? So I'm going to mark both of those, negative 2 and 3. In this region down here, x is less than negative 2, but it's also less than 3. So we're going to use the top rule for both cases, right? So in this region right here, f of x is going to be negative x minus 2 minus negative x plus 3 plus 1. Right? So here the function is negative x minus 2 minus minus negative x plus 3 plus 1. That whole thing simplifies quite a bit, right? Negative x minus negative x, those x's are going to cancel. Negative 2 minus 3 is negative 5, and negative 5 plus 1 is negative 4. So really in this region, the function value is negative 4. In this region between negative 2 and 3, right? Now we're going to use the bottom rule, right? Because x is greater than or equal to negative 2. But on absolute value of x minus 3, we're going to use the top rule still, because x is still less than 3 when we're inside of this region. So we're going to use this rule and this rule. So now f of x is going to be x plus 2. It's going to be x plus 2 minus negative x plus 3 plus 1. Now let's see what we get. We have x minus negative x. That's x plus x. So that's 2x. And then 2 minus 3 is negative 1 plus 1 is 0. So in this region, the function is 2x. Okay. And then finally, in this third region, x is greater than or equal to negative 2, but x is also greater than or equal to 3. So now we're going to be using the bottom functions, or the bottom rules, in both cases. So f of x is going to be x plus 2 minus x minus 3 plus 1. So let's simplify that. X minus x is 0, right? The x's cancel. 2 minus negative 3, that's 2 plus 3, which is 5, and 5 plus 1 is 6. So in this region, f of x is 6. So at this point, I could rewrite my function using that piecewise definition as follows. I'm going to have 3 pieces, right? F of x is going to be -4 if x is less than -2, right? If we're in this region right here, f of x is -4. F of x is going to be 2x if x is between -2 and 3, okay, including the -2, but not including 3. And then, right, that takes care of the middle region, right? We're between -2 and 3. And then in the third region, f of x is going to be 6. This happens if x is bigger than or equal to 3, right? That takes care of this third region here. X is bigger than or equal to 3. So this is the function, right? This is another way to express this function, right? So they are equivalent. So now if I wanted to graph these things, I'm going to start off by graphing f of x equals 2x between -2 and 3. So at -2, f of x is going to be -4. -2, -4. And then at 3, f of x is going to be at 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. I'm going to graph that with an open circle. Okay, and then it's just a straight line connecting those dots in between. So that's what this middle portion of the graph looks like, right? It gets us from x equals -2 to x equals 3. And then for x less than -2, so for x equals -3, -4, -5, whatever, f of x is going to equal -4. So at x equals -3, f of x is -4. At x equals negative whatever this is, f of x is -4. So you can see you get a horizontal line on that portion of the graph. And then by a similar line of reasoning, for x bigger than 3, so for x equals 3.5 or for x equals 5 or whatever, f of x is going to be 6. That goes this way. And actually, I can fill in the circle, right? Because this is true if x equals 3 as well. So when x equals 3, f of x is going to equal 6. So I'll fill that in. And that's what that function looks like. Let's convince ourselves of this by looking at it in Desmos. We had absolute value of x plus 2 minus absolute value of x minus 3 plus 1. Okay. And there you go, right? Sure enough, that looks pretty similar to what we graphed. Okay. Very good. So that's the idea there, right? You use these piecewise definitions to figure out, you know, what the function value is in each of the resulting regions, right? Okay. So that's how we would graph absolute value functions. Let's talk about solving some absolute value equations. So we're going to start off fairly simple. So let's, for example, let's look at something like absolute value of x plus 3 equals 7. We can't just subtract 3 from both sides. The 3 is trapped inside of the absolute value. And we can't distribute the absolute value or something like that. Like we can't say something like x plus 3 is equal to absolute value of x plus absolute value of 3. That's not true, right? That's not true. You could do some examples to convince yourself that that's not true, right? Like if you plug in, oh, I don't know, -1 for x, -1 plus 3 is -2. Absolute value of -2 is +2. If you plug it in over here, -1, absolute value of -1 is 1, absolute value of 3 is 3, 1 plus 3 is 4, right? So you can see that these two things are not the same. So we can't distribute the absolute value. We can't subtract the 3 when it's stuck inside of the absolute value. One thing that we could do that students often do, as a matter of fact, is just to ignore the absolute values. And if you ignore the absolute values, you do get one correct solution. You get x equals 4, which is correct, right? If you plug in 4, 4 plus 3 is 7, absolute value 7 is 7, so 4 works. But note that there's another solution. X equals negative 10 should also work, right? Negative 10 plus 3 is negative 7. Absolute value of negative 7 is positive 7. So how do we recover this solution? Well, note that if we can force the stuff on the inside of the absolute value to be either 7 or negative 7, then when we take the absolute value of it, we're going to get positive 7, just like we want. So that is, generally speaking, how we solve absolute value equations that are kind of simple like this, right? So we have a couple different cases, right? So if you have absolute value of some function is equal to some positive number, then it must be the case that the stuff inside the absolute value is equal to that number, or it's equal to the negative counterpart to that number. If, on the other hand, you have the absolute value of some function is equal to a negative number, right? If you say absolute value of some function is equal to a negative number, well, then that just has no solution, right? Because when you take the absolute value, you're going to get a positive result. So you're not going to get this equals a negative number, right? And then if you have a situation where you have, absolute value of something equals absolute value of something else, well, then it must be the case that the two things on the inside of the absolute values are exactly the same, or that they're off by a sign, right? So our strategy for solving absolute value functions is to get them to look like this or like this, and then apply these rules. So let me give you a couple examples. Here we have like a case 1 scenario, right? We have absolute value 3x plus 5 equals 4. So, and 4 is a positive number. So we can go ahead and apply this fact. We can say, okay, well, if absolute value of 3x plus 5 equals 4, then it should be the case that either 3x plus 5 equals 4, or that 3x plus 5 equals negative 4. Then we can just solve each of those equations independently, right? So I get 3x equals negative 1, x equals negative 1/3, or 3x equals negative 9, x equals negative 3. And so we have two solutions that should go into our solution set, negative 1/3 and negative 3, right? They're both solutions. Okay. Now part B, on the other hand, does not match this format because there's other stuff going on besides the absolute value, right? We have to solve for the absolute value first before we can apply one of these rules. So let's solve for the absolute value. We'll move this 3 over. We get 2 times absolute value 3x plus 5 equals 7 minus 3 is 4, right? And then we can divide through by the 2 and get absolute value of 3x plus 5 by itself, right, equal to 2. Now at this point, once again, this is looking like this case 1 scenario. And so we apply the case 1 rule. We say, okay, so 3x plus 5 equals 2, or 3x plus 5 equals negative 2. And then we finish solving from there, right? And that's that. Okay. Another example. Again, we need to solve for the absolute value before we can apply any other rules. So let's move the 3 over. Right, subtracting 3 from both sides, we end up with negative absolute value of x plus 5 equals negative 2. And you might be thinking, oh, you've got a negative number on the right-hand side. There's no solution to this, except that, look, you also have a negative over here, right? If you finish solving for the absolute value by dividing through by negative 1, then you get absolute value of x plus 5 equals positive 2. And so this has a couple of solutions, right? Okay. One last example. This is a case where you have a couple of functions on the inside of the absolute values that are equal to each other. So this is like that case 3 example from the previous page, but we can go ahead and say x minus 7 equals 2x minus 3, or x minus 7 equals negative 2x minus 3. You may be thinking, well, what about, aren't there some other cases? Like, shouldn't you consider if 2x minus 3 equals negative x minus 7? But that case would be exactly equivalent to this one. It's just, you know, divide both sides by -1 and you get this case. So you don't get any new information that way. Or you might think, well, why don't we consider negative x minus 7 equals negative 2x minus 3? But again, that's going to be equivalent to this first case. So no, all of the cases are handled just by looking at these two. So we finish solving. If I move the 2x over, and then if I move the 7 over, and then divide by -1. So I get x equals -4. Here I need to distribute that negative sign. Move the 2x over. Move the 7 over. Divide by 3. And there you go. Okay, so that's that. Now, that's how you solve these absolute value equations when you have one of these kind of like simple cases, right? What if you don't have a simple case? What if you have something that looks, say, you know, like this or like that? What do you do with those, right? Well, so for these kinds of equations, you have to use the piecewise definitions and consider cases, okay? So I'm going to take you through several examples of this so that we get the idea. And we're going to look at some graphs in Desmos to confirm that our solutions are correct, okay? So here we go. So if I want to solve x minus 2 plus 1, or absolute value of x minus 2 plus 1 equals x, well, one way that I could do it would be to say this. If x minus 2, well, maybe I'll say this, right? Absolute value of x minus 2 is negative x minus 2 if x minus 2 is less than 0, and then it's x minus 2 if x minus 2 is greater than or equal to 0. So that's equal to negative x plus 2 if x is less than 2, and x minus 2 if x is greater than or equal to 2, right? So what that tells me is that I need to consider two cases, right? I need to consider the case if x is less than 2, then I'm going to have, then this equation turns into negative x plus 2, right? Negative x plus 2 plus 1 equals x. If x is greater than or equal to 2, then this equation turns into x minus 2 plus 1 equals x. Okay, so then we can say negative x plus 3 equals x. If I subtract x from both sides, I get negative 2x plus 3 equals 0. Then if I move 3 over, I get negative 2x equals negative 3. And then divide by negative 2, x equals 3 halves. If I look at this case, then I'm going to have x minus 1 equals x. If I subtract x from both sides, I get negative 1 equals 0, which is a contradiction. right? So what that tells me is that this case doesn't give me any solutions, but this case does. So I just have one solution, and it's 3/2, right? Notice that 3/2 is less than 2. So my solution matches with the case that I started with. That's important, and you'll see why in the next part. But let's graph these two things to verify that they are that this is in fact the one and only solution. So I'm going to graph a couple things. I'm going to graph the left-hand side, which was x, absolute value of x minus 2. Whoops. Plus 1. And then I'm going to graph the right-hand side, which was just x. And the solution is where the graphs intersect, right? So there's the solution right there. And sure enough, right, 1.5, that's the same thing as 3/2, right? That's the solution. Okay. Let's look at another one. Absolute value 3x plus 2 equals 2x minus 5. So same deal. I'm going to say absolute value 3x plus 2. This is equal to negative 3x minus 2 if 3x plus 2 is less than 0. Or it's equal to 3x plus 2 if 3x plus 2 is greater than or equal to 0. So in other words, it's negative 3x minus 2 if x is less than negative 2/3, right? Move the 2 over, divide by 3. Or 3x plus 2 if x is greater than or equal to negative 2/3. So those are the cases that I need to consider. I need to consider if x is less than negative 2/3, then this equation becomes negative 3x minus 2 equals 2x minus 5. If x is greater than or equal to negative 2/3, greater than or equal to negative 2/3, then this equation becomes 3x plus 2 equals 2x minus 5. And let's see if we can solve this one. So move the 2x over, move the 2 over, divide by negative 5. Did I do that right? Negative 5x, add 2, negative 3. Okay, 3/5. Yep. You'll notice that this is a problem because this was the case when x was less than negative 2/3, and I'm saying if x is less than negative 2/3, then x has to equal 3/5. Well, that's a contradiction, right? That's not possible because 3/5 is bigger than negative 2/3, not less than negative 2/3. So that tells me that I don't get any useful information there. Let's try this one. I move the 2x over, move the 2 over. Okay. So here I get the statement that if x is bigger than or equal to negative 2/3, then x has to equal negative 7. Again, contradiction, right? Negative 7 is less than negative 2/3, so this doesn't make any sense at all. I think the conclusion I'm forced to arrive at is that there is no solution to this particular equation. We can verify that. Let's take a look at this in Desmos. So I'm going to graph the left-hand side, which is absolute value of 3x plus 2. And then I'm going to graph the right-hand side, which was 2x minus 5. And sure enough, look, no intersection, right? They're never going to intersect anywhere. In fact, they just get further and further apart the further out you go. So yeah, no solution. No solution. These two things are never equal to each other. So there's no solution. Let's do another one. 3x plus absolute value 3x plus 2 equals absolute value 2x plus 5. This is actually not even the kind that we have to do a piecewise definition. This is one of the simple versions, right? This is one of those simple cases where we can just say 3x plus 2 equals 2x plus 5, or 3x plus 2 equals negative 2x plus 5. So let's finish solving it. Move the 2x over. Move the 2 over. Distribute the negative, and then move the 2x over. And then move the 2 over. And then divide by 5. And that's that. Okay, we like these ones. we like the simple, straightforward ones, right? We can verify that these are the correct solutions, though, in Desmos. Right? We had absolute value 3x plus 2, and then we had absolute value 2x plus 5. And sure enough, right, we're getting two solutions here. One of them takes place at negative 1.4, which is the same thing as negative 7/5. The other one takes place at 3, right? So that confirms our suspicion, right? Okay, let's do part D. Now part D is really similar looking to part C, but there are no absolute values around the 2x plus 5. It's also really similar looking to part B, but in part B we did 2x minus 5, and we got no solution. So let's see, if we change that to 2x plus 5, will we get solutions? Will we get solutions this time, and if so, how many? Is there one solution, two solutions? Let's see. So I think I've already done a lot of the groundwork for the 3x plus 2 thing, right? So, so we know from our work in part B, that these are the two cases we have to consider, right? X less than negative 2/3 and x greater than or equal to negative 2/3. And what we realized is that if x was less than negative 2/3, then 3x plus 2 was really going to be negative 3x minus 2. If x was greater than or equal to negative 2/3, then 3x plus 2 was going to remain 3x plus 2. So let's finish solving each of these. Move the 2x over. Move the 2 over. Divide by negative 5. Does this make sense? Yeah, I mean, if so, negative 7/5, this is like negative 1.4, right? This is equal to negative 1.4. That's definitely less than negative 0.6 repeating forever, right? So, so yeah, this solution falls within this region. So, so it's a valid solution. Let's work on this one. Move the 2x over. Move the 2 over. Does this one make sense? Well, yeah, 3 is greater than negative 2/3, so that one also makes sense. So it's a valid solution. So I think they're both solutions. Same solution set as part C, although the functions look a little bit different, right? Let's take a look at Desmos. I realize I'm flying through these, by the way, but it's because this is a video. You can pause it, you can rewind it, so do so if you need to. But I'm going to take a look at Desmos. So on this one, we had absolute value 3x plus 2, and then we had 2x plus 5 not inside of absolute values. Okay, so that's what that scenario looks like. But you can see it doesn't change the solutions, because if I add the absolute values, all that's going to happen is that this little piece is going to start going up instead of continuing on its downward trajectory, right? So if I throw in absolute values, it just does that. So it doesn't change the solutions. Very good. Let's look at one more. Almost the same as part D, or actually not part D. It's almost the same as part C. But we've got an additional 1 hanging out on the outside. And that means that it's not a simple case where we can just do this. We have to do the whole piecewise business. And in this case, we're going to have to do the piecewise thing for two different chunks. So let's get to it. We already know that absolute value of 3x plus 2 is going to equal negative 3x minus 2 if x is less than negative 2/3. Or it's going to equal 3x plus 2 if x is greater than or equal to negative 2/3. What about absolute value of 2x plus 5? Well, that's going to work out similarly, right? Absolute value of 2x plus 5 is going to be negative 2x plus 5. If you distribute the negative sign, then you get negative 2x minus 5. It's going to be this if 2x plus 5 is less than 0. I'm going to do some scratch work. If 2x plus 5 is less than 0, that would mean 2x would have to be less than negative 5. That would mean x would have to be less than negative 5 halves. So I'm just going to say if x is less than negative 5 halves. And then it's going to be positive 2x plus 5 if x is greater than or equal to negative 5 halves. So there are our piecewise definitions. At this point, since I have a lot going on, and so I'm gonna draw a little number line just to help me keep track of all the moving parts. So this equation, right? It's gonna change rules at negative 5 halves and at negative 2/3. Negative 5 halves is smaller than negative 2/3. It's like this is negative 2.5 and this is negative 0.6. So negative 5 halves is maybe somewhere over here, and negative 2/3 is maybe somewhere right there. If I'm in this region, so this splits this, it splits the real numbers up into three sections, right? If I'm in this region over here, then I'm going to use the top rule for both of my pieces. So this equation is going to become negative 3x minus 2 equals negative 2x minus 5 plus 1. Negative 3x minus 2 equals negative 2x minus 5 plus 1. In this region, x is bigger than or equal to negative 5 halves, but it's still less than negative 2/3. So I'm going to use the bottom rule here and the top rule there. So that means this equation is going to be negative 3x minus 2 equals 2x plus 5 plus 1. And then finally, in this region right here, x is bigger than negative 5 halves, but x is also bigger than negative 2/3. So I'm going to use the bottom rule for both of these. So this equation is going to be 3x plus 2 equals 2x plus 5 plus 1. So let's solve each of those, okay? So negative 3x minus 2 equals, this is going to simplify down to negative 2x minus 4, right? I move the 2x over, so I add 2x, I get negative x minus 2 equals negative 4, and then add 2, negative x equals negative 2, and divide by negative 1, I get x equals 2. That doesn't make any sense, right? Because what I'm saying is that if I'm in this region, x has to be a positive 2. But positive 2 is like way over here somewhere, right? So no useful information there. Let's look at the middle region. For the middle region, I'm going to have negative 3x minus 2 equals 2x plus 6 is what it simplifies down to, right? I move the 2x over, move the 2 over, and then I divide by negative 5. get negative 8/5. Does that make sense? Is negative 8/5 inside of this region between negative 5/2 and negative 2/3? Well, let's see. Oh, I think so, right? Negative 8/5 is negative 1.6, right? So this is negative 1.6. This thing right here is negative 2.5, and this is like negative 0.6 repeating forever. So negative 1.6 is definitely inside of this region, for sure. So there's a solution. And now let's check this last one, right? So this last one is going to be 3x plus 2 equals 2x plus 6. Move the 2x over. Move the 2 over. I get x equals 4. Does that make sense? Is x equals 4 within this region? Yes, it is, right? 4 is definitely bigger than negative 2/3, so this looks like another valid solution to me. So I think my solution set should be negative 8/5 and 4. Let's take a look at Desmos to verify this. So on the left-hand side, we had absolute value of 3x plus 2. On the right-hand side, we should have absolute value 2x plus 5 plus 1. So it does indeed appear that we have two solutions. Now, what are they? Negative 1.6, right? That was negative 8/5, and 4. Sure enough. Okay. So there you go, right? That's how we deal with absolute value equations. And I think that does it for this section. Yeah. So we're done talking about absolute value functions for now. I do want to talk about absolute value inequalities, but we'll do that at the end of the chapter. I think the last couple sections in chapter 2 are all about the various kinds of inequalities we could be faced with. So that'll do it for absolute value functions for now. We'll see you in 2.2.